all for this NPTEL lecture on earthquake resistant design of foundation. And this is 24th lecture. And in this lecture, we will continue to discuss pile foundations, the third module of this course. And within the pile foundations, the last lecture we have discussed what is called CPRF, that is combined pile raft foundation. And in this lecture also, we are going to talk about the CPRF. That means this is the second lecture on CPRF. And in this lecture, we are going to talk about geotechnical and seismic analysis. Continue with this, what we have. So pile foundations and CPRF, second lecture, that is geotechnical analysis of CPRF and seismic analysis of CPRF. Before I go ahead, let me acknowledge that most of the contents of this lecture are taken from the following literature. It is a book entitled Foundation System for High-Rise Structures, published by CPRF, and these are the authors of this book. The speaker is gratefully acknowledge this contribution and thankful to the authors for this material. When we talk about geotechnical analysis of CPRF, this is discussed in three parts. One is ultimate limit state, second serviceability limit state, and third is pile load test. So let's talk about the first two limit states, which is ultimate limit state and serviceability limit. When we talk about ULS, the CPRF have to be analyzed in accordance to the internal and external bearing capacity. The analysis of the internal bearing capacity is conducted according to the corresponding standards. The analysis of the external bearing capacity is conducted under consideration of the time-dependent material behavior of the subsoil and the rigidity of the rising structure. The external bearing capacity is sufficient if the design value of the loads, which is represented by E subscript D, that is ED, is smaller or equal to the design resistance, that is R total D as. That means for external bearing capacity, ED should be less than or equal to R total DS. Now the issue is this one, that how to find that the design value of the resistance, that is R total subscript D, at a particular settlement, and that is defined by equation 1. And in this equation, R total K, as discussed earlier, is the characteristic load at a particular settlement, and gamma subscript RV is the safety factor for base failure resistance. So using this safety factor, we can find the design resistance, and the value of ED should be less than that design resistance. Continue with this philosophy of ultimate limit state. The total resistance of a CPRF is calculated for the whole foundation system, which consists of the foundation raft and the piles, and a separate geotechnical analysis of the single pile is not necessary. The characteristic resistance must be calculated by using a validated model, for example, numerical methods. In simple cases, the application of other methods, for example, analysis of base failure, is possible. Now, when we say about simple cases, there are some criteria of simple cases. One is simple geometry, which is, that means the pile length should be similar and diameter should be also similar. Constant pile spacing, a rectangular, quadratic or round foundation raft, homogeneous subsoil, no major differences of the stiffness, centric loads, no predominating dynamic loads. So in these cases, criteria of simple cases can be used. Now continue with that. When we talk about serviceability limit state, for the assessment of the suitability of a CPRF, a maximum settlement and a maximum settlement difference must be specified. In the context of the verification of the serviceability, the specified limit values must be proved under characteristic loads. So that means serviceability limit need to be checked under characteristic loads, not under design loads. The specified limit values for the deformation are defined by the rising structure as well as the neighboring buildings and the structures on the surface and under the surface. The analysis of the internal bearing capacity of SLS is conducted according to the corresponding standards and regulations. So this was regarding serviceability limit state. Now with that, next one is pile load test. When we talk about pile load test, why it is required for CPRF? For the design and the calculation of a CPRF, knowledge about the load deformation behavior of a free single pile is necessary. If there is no knowledge of the bearing capacity of piles for a special pile type in comparable soil conditions, a pile load test has to be performed. If a pile load test is not performed, then the bearing capacity of single pile can be estimated on the basis of empirical values, whereby this simplification and transferability has to be proved. Knowledge about the bearing capacity of a free single pile is important for two reasons. On the one hand, it is the only way to evaluate the selected geometries of the piles in accordance to the technical and environmental aspects, while on the other hand, it is possible to calibrate the numerical models. For complex construction projects or difficult soil conditions, in-situ pile load tests are strongly advised. So as far as possible, one should go for pile load tests. Now to conduct the pile load test, let's discuss one example where for the new construction of a high-rise building in soft subsoil, numerical simulations have been carried out for the design of a CPRF. And the calibration of the numerical simulation is based on the results of a pile load test, which has been carried out on the project area. For the loading mechanism, Osterberg cells were used. The test pile consisted of 3 segments, and these 3 segments are shown in the next figure. That is the upper test segment 1, the middle test segment 2, which is between the 2 O cells, and the lower test segment 3. So you could see here, you have on the top pile test segment 1, middle and the middle 2, and the last finally pile test segment 3. Between 1 and 2 segment, upper load cell is there. Between 2 and 3, you have lower load cells. And in this figure on the side, details of finite element mesh is shown here, which one can see that mesh is very fine near the center, but as you go away, then it becomes coarse mesh. So now the next issue comes that how to determine the base resistance and skin friction of the different soil layers. In that case, the individual O cells were activated in various testing phases. For example, for the test segment 3, for determination of the pile base resistance and skin friction, only the lowest O cell was activated, while test segment 2 was used in abutment. For the test segment 2, where we need to determine only the skin friction, not the base resistance, the upper O cell was activated, while the lower O cell was released. And in this testing phase, test segment 1 was used as the abutment. When you go for the post-test segment 1, that is the top one, and where you find only the base the skin friction, not the base resistance, again the upper O cell was activated and the lower O cell was stiffened. At the same time, the test segment 2 and 3 were used as abutments. So this is how we can find the base resistance and skin friction for different segments of the piles. Once it is done, then next is now let's discuss how to carry out seismic analysis of CPRF. And we are going to talk about this seismic analysis of CPRF under the 5 headings. First, let's discuss introduction. Then we are going to talk what are the advantages of CPRF under dynamic conditions, if you use the CPRF under dynamic conditions. Then numerical dynamic analysis. Then we are going to talk about steps for the design of CPRF. And finally, dynamic centrifuge test on piles and CPRF need to be discussed. So continue with that, let's discuss introduction, which is seismic analysis of CPRF. Seismic analysis of a CPRF is very complex and needs proper understanding of piles of soil raft interaction. The generalized CPRF model subjected to seismic excitation is shown in this figure. So you have raft, and then you have below this piles. The number of piles are there, and on the top of it you have what is called the loads coming from the superstructure. So this figure is showing a generalized CPRF model which is subjected to seismic excitation at the bedrock level. Then it could be the floating or friction piles because the pile tip is not situated on the bedrock. Now, when you want to analyze the CPRF, it is very complex because there is it requires the understanding of pile soil raft interaction. You have 3 components: piles and raft and soil, and the interaction among these components are have been already discussed in the last lecture. The lateral load induced on a CPRF during earthquake motion is jointly shared by raft and pile component. As the stiffness parameter and connection condition between pile and raft has to be defined carefully by performing what is called sensitivity analysis. continue with the introduction, it is observed by various researchers that the horizontal stiffness of a CPRF is larger than that of a pile group with the same configuration as that of CPRF. So if we have two things, one side pile group, on another side CPRF, configuration is same. However, the horizontal stiffness of CPRF will be greater compared to pile group. And this is the simple reason is here, because raft acts sufficiently as horizontal displacement reducer. Then coming to the bending moment of piles in a CPRF is less than that of piles in a pile group. So that is also advantage. The rotation of a CPRF increases as the rigidity of connection condition increases. So how it is changed? The horizontal load carried by a CPRF doesn't have significant influence on the pile head connection, where it has significant influence on the horizontal load proportion. Where the raft shares a large proportion of the load as the connection condition, rigidity increases. So if the connection is more rigid, then the more load is shared by the raft. The seismic analysis and design of CPRF is done by using the results obtained by centrifugal modeling, numerical simulations, and case studies. So with this introduction, now let's talk about what are the advantages of a CPRF under dynamic conditions. When you use CPRF for dynamic loads like earthquake or seismic loads, so first of all, improvement of serviceability of shallow foundation by reducing settlement, differential settlement, and tilt, and avoiding eccentricity and making load centric by concentrating piles around highly loaded area. So many advantages using CPRF. First of all, it will help you to decrease the total settlement and differential settlement as well as tilt. And because you can position your piles at the location where you have the heavy load, in that case, eccentricity can be easily avoided. Lateral load induced during dynamic condition will be shared by raft and pile. If a pile passes through liquefiable soil deposit, raft provides buckling stability to pile foundation in case pile is subjected to excessive axial load. Depending upon the loading condition, lateral load shared by the CPRF may be governed by designing the proper connection either as rigid, semi-rigid, or hinged. Various case studies show that CPRF performs better than other foundation systems in cases of seismic loading. In summary, CPRF is the most suitable foundation in seismically vulnerable areas. Now, when we talk about numerical dynamic analysis, the purpose of the numerical dynamic analysis of CPRF is to simulate in-situ soil conditions and to analyze the influence of dynamic loading on the various geotechnical structures with the help of an available numerical computer program. With the advances in the computers, the finite element analysis and finite difference analysis are gaining popularity and being applied more in the design of geotechnical structures. The invention of high-speed computers is encouraging geotechnical engineers to apply the finite element analysis for solving complicated dynamic problems. So finite element is quite popular nowadays to solve the problem. Different researchers have used different approaches for dynamic analysis of pile group, and pile raft foundations, which include the application of seismically induced lateral loads to the top of the pile head, or applying the acceleration force or displacement time speed at the base of a soil model to capture the response of such structures. Steps for the design of CPRF. Soil investigation data has to be properly checked before selecting any soil parameters and constitutive soil model to simulate realistic soil behavior. If stiffness parameters of soil are constant values, which is normally for the case of sand, then the Moore-Coulomb model is preferred choice. But if stiffness parameters of soil are varying with the depth, for example, in the case of soft clay, then care has to be taken in choosing the constitutive model to simulate actual field conditions. The hardening soil model and the soft clay constitutive model can be chosen. In case of to model the liquefaction condition, in that case, fin and Whitney models can be chosen, which are dependent upon the relative density and penetration resistance of soil. Continue with the CPRF. Steps for the design of CPRF. The size of the numerical model should be greater than about 2.5 times the length of longest pile for a static case, and should be increased further for lateral loading and seismic loading cases, and which can be done based on engineering judgment to eliminate the boundary effects. Pile spacing. pile diameter and pile position may be decided on the basis of the processor and parametric variation. Feasibility of CPRF must be checked based on settlement and differential settlement responses observed and compared with the conventional raft and pile foundation responses. For a structural component, that is raft and piles, high stiffness value has to be given as per the crustal strength of raft and pile material. So this was continuing this steps for the design of CPRF. Consideration of uniformly distributed loads may be useful for preliminary design and proportion of foundation components. So that can be done only for preliminary design. But for detailed design, you need to consider the actual distribution of the loads. Then seismically induced loads can be replaced by equivalent static horizontal load, which is equal to the seismic acceleration coefficient times the maximum load of the superstructure acting on the foundation unit. Else, alternatively, the real acceleration time stream may also be applied at the base of the soil model, and the response of the CPRF can be observed. Suitable CPRF codes like ISSMG combined pile raft foundation guidelines has to be followed properly for static design and can be updated further for seismic loading conditions. So this is possible that you can have the CPRF codes published by SSMG, but most of the codes, these are on static case, and then for dynamic case, you can extend the same. Now, talking about design of CPRF, the design of CPRF is performed by three-dimensional nonlinear finite element simulations. The length, diameter, and the number of the piles were optimized on the basis of the FE simulations, taking into account the requirements of the load deformation behavior. For example, in this figure, illustrate the optimized CPRF in the using the finite element simulation. Here, the CPRF coefficient, which is denoted by alpha versus CPRF, is 0.8, which means that 80% of the total load building weight is carried by the piles and 20% of the total building weight is carried by the raft. Full-scale pile and CPRF testing are very cumbersome and time-consuming, and simulation of an earthquake event in such tests makes it more complex. Therefore, to simulate the behavior of deep foundations under seismic loading, the numerical technique is one of the options, but to validate the numerical analysis, numerical data, one must have some field measured results. Hence, the need for dynamic centrifugal tests arises, which can simulate not only the state of the stress but also the event of liquefaction during the seismic event. Many researchers have done extensive tests on piles in CPRF to understand their behavior during an earthquake event. So now let's discuss some example from engineering practice. One example, a CPRF first of all is a technically and economically optimized foundation system, which is established in engineering practice, but it is still an open research topic. Numerous examples show its excellent applicability. The scope of application includes not only vertical loaded CPRF, but also horizontally loaded CPRF also. The following example demonstrate a construction project where the CPRFs were applied to realize an economical and reliable basis for high-rise structures. So what you could see in this example, this is from engineering practice. You have the message from in Frankfurt am Main, Germany, which is the city of the Germany. Its height is 256.5 meter high. It is founded on a CPRF in the Frankfurt clay. The foundation raft has a ground view of 58.8 meter into 58.8 meter with a maximum thickness of 6 meter in the center and thickness of 3 meter in the outer edge. So the raft foundation, the thickness is quite varying. It is 6 meter, quite thick in between, and then you have 3 meter at the edges. The base of the foundation raft is about 11 to 14 meters below the surface. So you have here base of the foundation, and which is below the surface. So this was one of the examples where the CPRF has been used. And with this, I conclude this lecture. Thank you very much for your kind attention.